So the next talk is by Satya Majumdar, but we're still waiting for the pictures.
Still wait.
Announced the title already. It's finite temperature, free fermions, and the Kardar-Paris-Zhang equation in infinite time.
Okay, so let me first start by thanking the organizers for the invitation, and it's been a great pleasure to be in this meeting. I've been here for more than 2 weeks now, and it was very, very nice. So, is this slide? Okay. All right. Just wait. Harmonic trap, where the second problem, which is the KPZ equation, which is, as you have heard from Herbert's talk before, that this is a classical non-equilibrium problem. So a priori, there is no connection between these two different problems, but what we find is that there is indeed a very curious connection between this equilibrium quantum problem and the classical non-equilibrium problem, and that is going to be the main thrust of my talk. So this is the recent work which was done in collaboration with David Dean at Bordeaux, Pierre Leduchal at École Normale Paris, and Gregory Scher, who is here, and these are published in these papers. And I would also like to acknowledge Christophe Salomon, who is an experimentalist in atomic physics in École Normale, because we really talked to him quite a lot about the possible experiments on this problem. Okay, so as you know, that there has been a lot of recent progress in the experimental manipulation of cold atoms. So cold atoms, it could be fermions or bosons, and they can do amazing things. They can tune the interaction between the atoms. They can tune the temperature. They can do many things. And in particular, these things have led to the investigation of the interplay between the quantum and the thermal behavior in many body systems at low temperature. So this is some kind of revival of quantum statistical mechanics in recent years. And typically, in a setup in this cold atom system, what you have is a harmonic trap, laser trap created by lasers. And you have some particles in this, which could be fermions or bosons. And as I said, they can basically, using, for example, phase-back resonance, they can tune the interaction between these particles. And these are quantum particles. And they can also, change the dimension of the trap. They can change the temperature, so they can, explore many beautiful things in these experiments. And so what we would like to understand is actually a very basic question, which is the case when these are fermions and they are totally non-interacting, which means the only interaction is that they are quantum particles, meaning that they satisfy Pauli exclusion principle. No two particles can be in the same quantum state, single particle state. Okay? So that's the system I'm going to focus on, and it's the simplest, very simplest system. So you have a harmonic trap with a potential which is like this. Let's say for the moment is one dimension. And I have a bunch of fermions which are sitting on this line in this trap. And these are spinless fermions. And now this problem, if you're at zero temperature, so these particles still have quantum fluctuations. And what you can show, and this is what I'm going to show you first, is that there is a beautiful connection between these spinless free fermions and in the harmonic trap at zero temperature and the random matrix theory of Gaussian unitary ensemble. That means if you take a complex Hermitian matrix with Gaussian entries, which is called the Gaussian unitary ensemble. So a lot is known about the spectral statistics of this random matrix theory. And what we'll see is that the positions of these free fermions in a harmonic trap at zero temperature are in one-to-one correspondence with the eigenvalues of this random matrix theory. So using the known results from random matrix theory, we can say a lot about this spinless free fermions in 1D harmonic potential at zero temperature. And in this talk, so that is a sort of known result from random matrix theory. We'll just lift these results, but we'll go beyond. So what we want to study is what happens when you increase the temperature, okay? And then there's no connection to random matrix theory a priori. And also we want to see what happens when you have a trap which is not one-dimensional, but let's say two-dimensional or three-dimensional, because experimentally you can actually manufacture such traps, okay? So that's the sort of main talk. And so here's the outline of my talk. So first I will focus on D equal to 1, in D equal to 1 and zero temperature. And I'll show you the connection to random matrix theory. And then I'll consider the finite temperature. And we'll see there's this curious connection, mathematical connection. We still do not understand what is the sort of deep physical reason behind this connection of the KPZ equation and these free fermions in D equal to 1. I don't think I'll have time to give you the derivation of these results. And then finally, I'll talk about extension to higher dimensions. I'll just give you the results and I'll conclude. Okay, so that's the outline. So let's start with a very, very simple problem. Everybody in this audience, whoever has done undergraduate quantum mechanics knows this. So let's think of just a single particle, single quantum particle in harmonic potential. This is the first undergraduate exercise you do. You just solve the Schrodinger equation in this potential. And you know that these single particle eigenfunctions, they are just Gaussian times Hermite polynomial. So this alpha here is the square root of m omega bar by h bar. So that's the quantum fluctuation length scale. And the energy levels are quantized, of course, and they're just given by k plus half h bar omega, where k is a positive integer, 0 to infinity, and just a solution of Schrodinger equation. Okay, and these are Hermite polynomials, which I have written down on the board for you. And so these are the all single particle states, and these are explicit single particle wave functions. Okay, so if you are at 0 temperature, for example, then k equal to 0 is the ground state, which means that this is 1, so it's just a Gaussian. And this Gaussian, the width of this Gaussian, inverse width of this Gaussian fluctuation specifies the quantum fluctuations here. So it's at 0 temperature, but still there is a fluctuation due to quantum mechanics. Okay. So this is everybody knows. So now I'm going to put this is the Hermite polynomial. Now I'm going to put n particles, n spinless free fermions. Okay. So there is no interaction between them. The only interaction is that they have to satisfy Pauli exclusion principle. So I have this harmonic trap. Instead of 1 electron, I have n electrons now, and they're still at all 0 temperature. Okay? So these are my single particle levels given by this object here. And so what do you do? How do you construct such a many-body state? You just fill up the electrons up to the Fermi level, which is up to k equal to 0 to n minus 1. And you want to construct the many-body ground state wave function, which I denote by capital psi 0. And this is, everybody knows, this is again the basic thing, which is that this is what is called the Slater determinant. That means this many-body wave function has the property, because of Pauli exclusion principle, that whenever any two coordinates become equal, it should vanish. And the way to construct this is to antisymmetrize these single particle wave functions. And so you have a determinant, and this is called the Slater determinant. Okay? And where the entries of the Slater determinant are just these single particle eigenfunctions. Okay? So this is a very standard stuff. And this object here specifies the quantum fluctuations of this many-body system at 0 temperature. Okay? And the ground state energy, of course, you just add up the energies of all these guys, is just n square over 2. All right, so this is a very basic stuff. And so let's see what it gives. So I have this ground state wave function. And so what you see is that if you substitute these single particle wave functions here and calculate this determinant, these Gaussian factors just go out of here. And what you have is a determinant of the Hermite polynomial of degree I. Okay? But determinant of Hermite polynomial, as I wrote in the board here, it's actually very, very simple. So these are Hermite polynomials. I give the example for n equal to 3. So you just calculate, you have 3 particles, x1, x2, x3. So this is the determinant of this Hermite polynomial of 3 by 3. So this is very easy. So you just multiply this row by 2 and add this, and take out the numerical factors, and you can see that immediately you can reduce it to a van der Waals determinant, which is 1, 1, 1, x1, x2, x3, x1 square, x2 square, x3 square. So this is explicitly you can evaluate, and this goes through for any n, not just n equal to 3. So determinant of Hermite polynomial is always a van der Waals determinant, and you can therefore calculate it explicitly. And so that's the sort of answer for the explicit answer for the many-body wave function. And so in quantum mechanics, of course, this mod square is like the quantum probability, if you like. Okay, so this sort of indicates the quantum fluctuation probability that the particles at 0 temperature will be at position x1, x2, x3, xn. So it's given by the square of this, and so you have an explicit answer for this. Okay, now this is precisely the distribution of the eigenvalues of a n by n random Hermitian matrix with Gaussian entries. So those of you who are not familiar with random matrix theory, all you have to do, you just take an n by n Gaussian, n by n random matrix, and it's a complex Hermitian matrix. So you have to take the real and imaginary parts of the upper diagonal things and choose them as Gaussian entries. And then, of course, you can calculate what is the joint distribution of eigenvalues of such a matrix. All the eigenvalues are real, so there will be n real eigenvalues, and you can calculate, and it's well known from books on random matrix theory, for example Mehta's book and Dyson's, this is Wigner-Dyson distribution. So the joint distribution is known to be lambda I minus lambda j square times exponential minus summation x lambda I square. So what you see is that there is one-to-one correspondence. The quantum fluctuation at zero temperature of these n free fermions, they are in one-to-one correspondence up to a rescaling factor alpha to the eigenvalues of a Gaussian GUE random matrix, basically. Okay, and so this joint distribution in the RMT random matrix theory have been studied, ad infinitum. There's a lot is known, and so we can just directly lift these results to calculate the observables in this quantum problem. Okay, and this has been done in recent times in various papers. So the various spatial properties of these free fermions in a harmonic trap at zero temperature, we can directly obtain from the known results in random matrix theory. And okay, I'll not tell you about everything, but just list a few properties which are quite interesting. So first thing is the average density of free fermions. So you have these fermions in a trap, and you ask, okay, if I look at between point x and x plus dx, what's the fraction of particles between x and x plus dx? So that's the average density on an average. So this is defined by this object. So I have this joint distribution. So this angular average is with respect to this joint distribution. And so this is exactly the density of eigenvalues in the random matrix theory. And it's well known that this density is given by this Wigner semicircular form. So it's a scaling form. So each of the eigenvalues scales like square root of n. So if you scale by n, then this is a scaling function which has the famous Wigner semicircular form with a square root of 2. It's a bounded support between minus square root of 2 to plus square root of 2. So basically it says that all the eigenvalues of the random matrix, or if you like the fermions, you have a harmonic trap. So they like to come closer together near this trap center, but there is a repulsion because of Pauli exclusion principle, or which is also encoded in this van der Monde term. You can see that, this van der Monde term, which says that the probability that two particles come very close to each other goes to 0. So this is called the level repulsion. So there is effective repulsion, logarithmic repulsion between these particles, and so as a result, on an average, the fermions, they settle down in the trap center, near this trap center over a finite region, and this is the famous Wigner semicircular law. Okay, and this sort of result can also be in the atomic physics. People typically derive these results by using the Thomas Fermi approximation, but you can actually get the exact results just from the one-to-one correspondence to random matrix theory. Okay, so this is the average density. But one thing which the atomic physics people don't know, they usually look at the bulk properties, but they don't care so much about the age properties. But what is known from random matrix theory is that there are a lot of universal properties near the edge, and those are the new things that you can bring from RMT to this atomic physics literature, and that's what I'm going to tell you now about. Okay, so the density goes to 0. So because so basically it means that lots of particles near the center. The typical distance, interparticle distance, is of order 1 over square root of n, because this is from minus square root of 2n to plus square root of 2n. So you are packing n particles. So the average interparticle distance in the bulk is 1 over square root of n. Whereas as you go towards the edge, they become sparser and sparser, few particles, and the typical separation between the particles there actually are much larger than 1 over square root of n. And so what happens is, as you go towards the edge, okay, of the semicircular law, so let me just draw it here for you. So this is on an average. Okay. So here, in this edge regime, the typical separation between particles is of order n to the power minus 1/6, whereas near the bulk, the typical separation between particles is of order n to the power minus half. So for large n, this is much bigger. The particles become sparser and sparser as you go towards the edge, and the typical width of the edge regime is of order n to the power minus 1/6. So if you actually go towards the edge, so this is the average density, but if you go actually look at for a finite but large n system, and if you look at the distance from the edge and scale it over this scale, length scale, then you find that this is a universal scaling function. So that this describes the scaling function when you look at a finer scale, zoom in the edge regime on a scale of n to the power minus 1/6, and if you look at the density there, so this density has a universal scaling form, which is called the, which is just related to the Airy function, and this was first calculated by Breza and Bowick and also by Forrester. So this is the function. So basically, in the large n limit, all these oscillations, just die out, and you see average weakness semicycle. But if you go and zoom in, you find these oscillations, and you find this tail here, and here on the left side it goes like square root of z in order to match with the bulk weakness semicircular law. So these are all old results from the late 90s and early 90s. And the other point that Joel also mentioned, which is that if you actually calculate now not just the average density, but endpoint correlation function, by that I mean you take this joint distribution and you integrate out n minus n coordinates and look at the marginal of the first n coordinates. Okay, so this is called the endpoint correlation function. There is a combinatorial factor just for convenience. And so what happens here, for example, the 2-point function is just this guy. What's the probability of having one fermion at y, another fermion at z, and in general, n-point correlation function. So what happens here in this problem of the GUE random matrix or these fermions, you can show that the endpoint correlation function you can write as a determinant of an object which is just called the kernel, and this kernel is just the single particular wave functions summed over k to 0 n minus 1. So these are just the Hermite polynomial time Gaussians. And so if you know this kernel, that's the sort of central object, that's a basic building block. If you know this kernel, you know any endpoint correlation function, including the average density, which is just the kernel itself, because little n equal to 1 is the average density, it's marginal. So therefore, if you know the kernel, you know everything. And these are processes which are called the determinantal processes, as Joel was mentioning. So basically, if you can write down the joint distribution as a determinant, and if this determinant satisfies some additivity property, then you can show that any endpoint correlation function you can write as a determinant. And the basic object, therefore, is this kernel. So if you know the kernel, you know everything in these systems. Okay. So this is a special property of the zero temperature free fermions, or GUE eigenvalues, if you like. So what do we know about the kernel? So you can, next question is that, in large n limit, how does the kernel behave? And so you can actually, as I said, average density is just the kernel itself at identical points xx. So the main point is to then calculate this kernel, because if I know this, I know everything. And this has been done. And what is known, I'm just telling you the results from random matrix theory. So basically, if I'm in the bulk, near the center of the trap, so there it has a scaling form here, and this scale is essentially, it's 1 over square root of n, and this function looks like just sine 2z over pi z. So this is the famous sine kernel. On the other hand, if you go towards the edge and you take 2 points, both points in this edge regime, and you scale over the scale of n to the power minus 1/6, then this is again universal scaling function, and this function has this form. This is the Airy function at A, Airy function at B, A prime at B, minus this. So this is what is called the Airy kernel that Herbert also talked about in his Chandrasekhar lecture. Okay, so these are sort of well-known results that the bulk, the kernel has a particular scaling form, which is called the sine kernel, and whereas near the edge, it has a slightly different form, which is called the Airy kernel. Okay, very good. So this is all known results from random matrix theory. And the another interesting result is, of course, you can ask, what is the position of the rightmost fermion in this language? Okay, so this is the x max. And again, we know from random matrix theory that, okay, this is, as I said, from the one-to-one mapping, you see at zero temperature, this position of the rightmost fermion is exactly same, has the same identical probability law as the largest eigenvalue of a GUE random matrix. And this is therefore governed by the so-called Tracy-Widom distribution. And what is Tracy-Widom distribution? Basically, it says that the cumulative distribution, probability that the x max is less than or equal to some number m, is just a scaling function of m minus this edge. Our edge is the square root of 2n over alpha divided by this typical length scale n to the power minus 1/6. And this scaling function you can write as a Fredholm determinant. So it's a formal object. I'm not going to give you the detail. Basically, essentially, if you know the edge kernel, in principle, you know this scaling function. And what Tracy and Widom did is they could calculate, show that this actually satisfies a second order nonlinear Panleve 2 equation, and they could get the asymptotics. It's so everything is known about this position of the rightmost particle. Okay, so basically again, once we know the kernel, I know, a lot of things about the properties of the system, correlation function, distribution of the largest eigenvalue, and therefore you can lift all those results from random matrix theory to say something about the fermions at zero temperature in this harmonic trap. So in most of the experiments in cold atoms, people look at the bulk properties, and what we are telling them that no, you should look at the age properties as well, because there are universal things that we can predict from random matrix theory, and you should be able to measure these objects. Okay. So here's the summary then. So essentially at zero temperature, this problem is a determinantal process, meaning that any endpoint correlation function I can write down as a determinant of a kernel. And this kernel has this property that in the bulk it has a scaling form, and the edge it has another scaling form in terms of this sine and array kernel. And it's also universal in the sense it does not depend whether, I did the calculation for harmonic well, but actually it turns out that you can take any confining potential mod x to the power p, where p can be any positive number with a single minimum. And this array kernel, for example, or the bulk kernel, they are completely universal. They do not depend on the precise shape of this potential. Okay, so this is also known. Okay, so far I was talking about the zero temperature problem. So now we want to know what happens at finite temperature, okay, as you increase. So here there is no one-to-one correspondence to random matrix theory. So we have to say, do some new calculation. What do we do? So what happens at finite temperature? So basically, zero temperature, you have all these fermions going up to level 0 to n-1. So when you go to finite temperature, so then you can choose your n single particle states to be one in which one electron you just fill up this level, and there's a gap here. This is one possible states, for example. Okay, so you can have many possible steps. And okay, this is a sort of complicated formula. It's not that complicated, but basically normally ground state means that you take the first n single particle states, okay? But you can take one electron and just consider another single particle state, and you can construct the determinant, the Slater determinant of that many body state with a given energy, and the energy of that state will be just sum of the single particle energies which are occupied, okay? And therefore, at finite temperature, all you have to do is to take this object and multiply by the Boltzmann weight, e to the power minus beta e, and divided by the partition function, which is just this guy. Okay, so essentially, all that happens at zero temperature, of course, only the ground state is chosen. So you have the usual Slater determinant of the first n single particle states, and now you just have to fill up all possible states with occupation numbers, and this determinant is basically determinant of the single particle levels that are occupied. Okay. But they are explicit. They are just the Hermite polynomials, and so I'm not going to go through the details of this calculation. But this is the sort of main central object, and you have to deal with this. And so I'll just tell you the results. Essentially, I'm not if I don't have time. So you can calculate the average. First thing is to calculate the average density. So average density, of course, there are two very well understood limits. So as I said, zero temperature, this should reduce to the Wigner's semicircular law, as I described just now. Now at finite temperature, on the other hand, at infinite temperature, you would expect that these fermions, they don't see the Pauli exclusion principle. So each of them is like a Maxwell gas. So each of them is like a Gaussian distribution, and you would expect that the density should go to a Gaussian form, and with a beta being inverse temperature. So the question is, how does this system evolve from this Wigner's semicircular law, which is a bounded support, to this Gaussian form as you increase the temperature? Okay, how do you go from Wigner's semicircle to Boltzmann-Gibbs distribution? Okay, so how do you interpolate at finite temperature, basically? And this is our sort of main result. So what you find is that there are two natural dimensionless variables in this problem. So one is the Fermi energy, which is just proportional to n times h bar omega, divided by t. So this is a dimensionless variable, I call it y. And another dimensionless variable is just x over square root of m omega square over 2t. So in terms of these two variables, you can actually find that in the limit when n is large and the t is of order n, so that you fix these scaling variables y and z and take the large n limit, and then you find that this density is given by a scaling form. So it's a scaling function of these two dimensionless variables, and the scaling function is explicitly given in terms of this polylog function. Okay, and you can check that in the two limits you recover the. So here is some picture. So you can check that in the two limits, when temperature goes to 0, you recover the Wigner's semicircular law. whereas in the infinite temperature limit, you get back the Gibbs-Boltzmann distribution. Okay? So this is the first result which was in this paper, and so this is very nice. So we are very happy. This is just the average density, and then you can ask, okay, what happens to endpoint correlation functions? And okay, so this is just okay. First thing, okay, before we go to correlation function, we can also ask at 0 temperature there is a specific edge, and you saw that there is a scaling function near the edge, and you can ask what happens at finite temperature. Okay, so what's the sort of generalization of the Breza-Bawick result? Okay, so it turns out that at finite temperature, so there is a width here. It's of order n to the power. When you scale the temperature as n to the power 1/3, and so you find that this rho n xt, the density near the edge at finite temperature. Now there is no fixed edge, but there is a sort of very smearing function, and this scaling function at finite temperature is precisely given by this by this functional form, where this constant b is related to is just temperature times n to the power 1/temperature times n to the power 1/3. Okay, so you can analyze what happens at finite temperature near the edge and the density. So this is just a direct generalization of the Breza-Bawick formula. Okay, and so this is just a plot of this function. So this is at 0 temperature, and you see that as you increase finite temperature, then this b is finite, and then it has different form, and it has these asymptotic behaviors, which is square root of z in order to match the Wigner semicircle, bulk result, and it decays exponentially. At 0 temperature, this guy decays exponentially e to the power minus z to the power 3/2, whereas at finite temperature, it actually decays like exponential minus bz, where once again this b is just temperature times n to the power minus 1/3. That's a sort of new scaling variable that emerges when we analyze near the edge. Okay, so this is the density. So we understand density, the bulk, and the edge at finite temperature, and then you can ask what happened to correlation kernel. So it turns out that, here we are looking at the canonical ensemble where the number of particles is fixed. But in order to make progress, it's easier to actually look at the grand canonical ensemble where you just multiply, just take the Laplace transform or generating function where mu is the chemical potential, which is fixed. And then in the large n limit, what you can show is that, this grand canonical ensemble for any finite n actually also has the determinantal structure. And since in the large n limit, these two ensembles are equivalent, so this is our original ensemble. So at the large n limit, what happens, even at finite temperature, that this process, the many body quantum probability joint distribution essentially becomes a determinantal process. Okay, so that's the sort of main observation. That this determinantal structure even persists even at finite temperature, but the kernel changes. Kernel now has this form. Again, these are the single particle Gaussian times Hermite polynomials, but you have this extra Fermi factor which comes in, and this is quite normal because you would expect that the occupation numbers essentially contribute to the Fermi factor, and so that's the sort of you can show this rigorously here, and this is the sort of main new results. And of course, if you take the 0 temperature limit, beta goes to infinity, and you get back the correlation kernel at the 0 temperature. Okay, so this is the finite temperature generalization of that this kernel, and then all you have to do is to analyze this kernel near the edge and near the bulk, like we did at 0 temperature. Okay, and interestingly, this same object also appears in some classical random matrix models, which have been, but there is doesn't have the interpretation of temperature. It has something else, but in a similar functional form appears also. All right. So let's try to analyze this kernel. So what happens is that in the bulk, again, if you are deep inside the bulk, you have again a scaling form. Now this is a which is a little bit complicated function, but this is a direct generalization of the sine kernel. My time is up. Okay, direct generalization of the sine kernel. 10 minutes. Okay. And again, you can check that these are universal. Okay, that is, it doesn't matter whether it's a just a harmonic well or something else. And this is the bulk. And if you come to the edge, once again, you have to scale the regime as n to the power 1/3. Okay, and you take 2 points very close to the edge, and you analyze this object. So it's just a very simple object. It's just a Hermite polynomial term Gaussian multiplied by a Fermi factor, and you just have to analyze this object. Okay, and you do that, and you find that this has a scaling form again, like in the 0 temperature, except that this edge kernel has this particular form, which is airy times airy. So A and B are the scaled lengths here, and there is this Fermi factor e to the power minus beta u plus 1. And so this is the generalization of the finite temperature generalization of the airy kernel. And once again, you can prove that this is, it's universal in the sense it does not matter on the detailed shape of the confining potential. Okay. And okay, so you have this airy kernel at finite temperature, the generalization of these things. But this particular kernel also appears very famously in the KPZ problem, which I'm going to talk about now. But before that, let's just think of also the rightmost fermion. So I can ask the same question as I asked in zero temperature. What's the distribution of the rightmost fermion? And so the answer would be exactly that. Again, this is the cumulative distribution of this is some scaling function of m minus rh over wn. Again, wn is of order n to the power minus 1/6. And this function, again, you can write as a Fredholm determinant. So this is directly a generalization of the Tracy-Widom distribution to finite temperature. And this kernel is precisely given by this generalization of the airy kernel. Okay? So this is our sort of main result. So we know everything about finite temperature now. But then let's look at this kernel here. I mean, you have those of you who were there in Herbert's Chandrasekhar lecture, you have seen the exactly same kernel also appears in the KPZ problem. So let me just remind you what KPZ problem is. So you have heard this many times in many talks. So you have this height is a classical problem out of equilibrium. So del H del T, there's a diffusive term, there's a nonlinear term, and there's a noise term. And you start from this wedge initial condition, which is minus mod x over delta. And then as time goes, this surface smoothens, and you can ask, what is the height distribution of this? And as you have heard, and you will probably hear next week from Tomohiro's talk, his lectures, that he's going to tell you exactly how to solve this problem for the height distribution exactly. So these are, a series of works in the last few years. You know everything about this KPZ equation, and what came out of these problems is that if you look at the generating function of this height, so here this gamma t is just, this is time, t to the 1/3. And if you look at this particular generating function, so this is just, generating function of the height, or Laplace transform if you like, but it's a strange generating function, it's a Gumbel form. Then this object here, you can write again formally as a Fredholm determinant, and the kernel that appears in the Fredholm determinant has exactly same form, and here this gamma t is just the time to the power 1/3. Okay? So you see that this is precisely the problem also appears in our quantum equilibrium problem of n-free fermions at finite temperature. So therefore, time here, so when you take the t going to infinity limit, you get back the usual airy kernel. But so basically, there is a time acts like the okay. So this is the correspondence. So time in the KPZ problem, finite time, is like the inverse temperature in the free fermion problem. So it's exactly same form, both problems. Okay. But this is a weird object. I mean, this is sort of height generating function, and this is a sort of scaled height. And but the same kernel appears. So all that happens here is this is just a temperature, and here this is related to time. Okay, so this is the precise relation. So infinite time is like zero temperature limit, and finite time is like finite temperature limit. Okay, so this is the sort of main quantity. So this is the sort of main result, that basically you can say everything about finite temperature in this problem, and they are universal in the sense they do not depend on the details of the potential. Okay, so I'm going to sketch skip the derivation, just tell you what happens at higher dimensions. So let me just sketch this, get rid of this. Okay, so let's talk about higher dimensions in the last 2 minutes. So if I have a higher dimensional trap like this, let's say harmonic trap, but x1 square plus up to xd square. And again, you can work it out, the global density. So these are slightly different techniques. There is no random matrix connection here, but we can still work out the details. And the density, this is just a higher dimensional generation of the Wigner's semicircular law. So you find that this mu is the Fermi level. This is basically proportional to n to the power 1 over d. And so what you have, so in 1D you had just this Wigner's semicircular law, and here you have a like a cup basically in higher dimension, and the large n limit, it goes into this particular form, which is constant minus r squared to the power d over 2. And then you can actually work out the edge kernel as well, and it also has a determinantal structure. Okay, at so I'm talking still at 0 temperature. So you can calculate what is the edge density. So edge density has this particular form, explicit form, and the width of the edge regime is n to the power minus 1 over 6d, d being the dimension. And the scaling function also depends on d, and again universal, but depends on d explicitly. So this is just a direct, d-dimensional generation of the result of Breza and Bowick and Forrester. So one dimension, this is this form, but in d dimension, it has this particular form. Okay, so here these results for this function here. You can see the edge density, and it has these asymptotics which you can work it out explicitly from this object. Okay, so this is the edge density, and again, as I said, the kernel also has the determinantal structure, and so I mean the endpoint correlation function. You can calculate the bulk kernel, which is just a Bessel function. This is a generalization of the sign kernel in 1D. And also you can calculate the edge kernel, which has a little bit more complicated formula. And here, if you put d equal to 1, you get back the standard airy kernel. But okay, you have some more complicated form here, but you can calculate everything. Okay? Yes. N to the power d over 2. Yeah. Sorry. Yeah. This is this mu is n to the power 1 over d. So n to the power 1 over 2d basically. Okay, so that more or less ends my talk. So let me just go to the conclusion. So basically, what you can do is that you can derive some exact results for the free fermions in d equal to 1 at finite temperatures. As I said, at 0 temperature, there is a 1-to-1 correspondence to the RMT, random matrix theory. So you can lift the results. But at finite temperature, there is no analog of RMT, but you can still do the calculations. And you find this very nice explicit formula, and in particular it has this determinantal structure at finite temperature. And what we see is that near the edge, the kernel that describes the asymptotic form of this the behavior near the edge. So that kernel at finite temperature has exactly same form as the finite time kernel in the KPZ equation, although there is no direct connection between these two problems. So this is a sort of open problem, and we observe this, but we really do not understand, what is the connection, because I don't see any height evolution in the free fermion problem. So this is something to be explored and understood, and of course we can do the generalization to higher dimensions, and higher dimensions as well. And once again, I stress that these are universality of these new kernels. That is, they do not depend on the trapping potential, and as long as you have a simple confining potential. And then you can ask, okay, in higher dimensions at finite temperature, so this we can also work it out. I'm not going to give the details. And the last question, and this is where we are now discussing with Christoph Salomon, that can one observe these kernels or these edge properties? So basically, as I said, in the cold atoms experiments, they typically look at the bulk behavior, and so far nobody thought about really probing the universal behavior near the edge, and this is what we are telling them. And so now with this Fermi microscope, so if this is true, this is true. So this is going to be the simplest measurement of Tracy-Widom distribution. Basically, you just look at the rightmost fermion at 0 temperature and just measure its PDF. Basically, that's it. And you don't have to go through the liquid crystal. Liquid crystal is experiments of Takeuchi is very nice, but this is for the KPZ equation. This is not directly for the random matrix. Okay, but this is direct verification of the results. And then you can ask, they can of course tune the temperature, they can tune the interaction. So there's a whole lot of new areas which opens up with this, and we hope that they will be able to measure these things in these experiments. Okay, so thank you very much.
So there's time for some questions. I think you were the first.
Yeah. So because you started with a simple harmonic oscillator.
Sure.
Model. So I have a question which is a bit too speculative, but maybe
Sure.
interesting.
Yeah.
So if we solve this quantum Hall problem,
Yes.
integer quantum Hall problem.
Yes.
So effectively, on the equations, it finally reduces to simple harmonic oscillator.
Right.
And if you look at the wave functions, let us say we solve it in the symmetric gauge.
Yes.
Then you have at center, so you have a Gaussian.
Mm-hmm.
Then you have some small circles.
This
with
edge currents,
density
right,
which
yeah.
goes as the Gaussian.
Right. Yeah.
The only difference between the 1D harmonic oscillator and that is
Absolutely.
that here you have degeneracy which goes like the area of the
Sure. No, in fact, I mean, quantum Hall effect, I mean, this is more like the sort of Geneva ensemble, which is if you take a, just a, n by n matrix,
Yes.
and if you look at, there's no symmetry between them, okay, and you take this, to be random, Joel talked about that. So there also, if you take them to complex Gaussian variables, you can actually work out the joint distribution, and they are more like the Laughlin wave functions in quantum Hall effect.
Exactly, that's what I was trying to come to.
Absolutely, yeah, they're more likely Laughlin wave functions, and so you can again ask these questions at age properties and other things, and so there are many things that you can ask. It's a simple observation that essentially Slater determinants are in fact, I mean, random matrix literature. It has been well developed by Mehta, Dyson, and other people, and this is a so-called famous orthogonal polynomial method. But the orthogonal polynomial method is nothing but just this doing single particle harmonic polynomial quantum mechanics problem, basically. Just a many-body, just a Slater determinant. So the fact that the Slater determinant is there is I mean, they don't have to. They develop the orthogonal polynomial method, but this is just quantum mechanics. I mean, phi kx are orthogonal, and they have the polynomial Gaussian times polynomial structure. So it's exactly same, I mean, essentially. Yeah.
So what about the integer, fractional quantum Hall effect? So
yes.
can one
So I mean, yeah, there of course the other problem is you have a disorder. I mean, the fractional quantum Hall effect, you always have disorder, and then of course I mean, I don't know if you can write down explicitly this kind of joint distributions of the or Slater determinant square. If you can do that, probably you can make many advances. But I mean, this is not so well known whether you can write down all the wave function explicitly for fractional quantum Hall effect. Yeah.
Yeah, I have two small questions.
Yeah.
One, could you do the same for bosons with hard
Okay, that's a good question. Well, bosons are essentially, see, if you are at zero temperature, for example, simplicity, okay? So essentially, the boson wave function will be just the product of the, single particle wave functions because it's symmetric. There's no anti-symmetry. There's no Pauli exclusion principle in bosons, okay? So basically what happens is it's like ideal Bose gas, basically. So you can have, depending on your trap frequency, you can even have in one-dimensional Bose-Einstein condensation. If you increase the temperature, or reduce the temperature, then at some point, all the particles might condense onto the ground state, for example.
It's even true with repulsion between them.
Yes. No, there is no repulsion between them, bosons, right? In quantum mechanics problem, there is no repulsion between bosons.
Potential between.
No, I mean, I'm talking about the non-interacting limit. Of course, you can, surely. I mean, you can actually tune the interaction and, put direct repulsion between them. But here I'm talking about even the very simple non-interacting limit. So fermions, it's just a quantum statistics, basically, okay? But you can actually, of course, put in direct interaction. You can ask what happens when I put, in fact, this is exactly one of the things that they want to explore in experiments, that, if you put in interaction, then how much of these universalities still hold, essentially, okay? And, I mean, probably, if you have a short-range interaction, it should not matter. I mean, that's the sort of, belief, basically.
Second question,
yes.
Are your results directly related to this distribution of steps around the corner of an equilibrium crystal shape?
Yes. So because again, equilibrium crystal shapes. If you look at the the steps basically, and if you look at the and the only constraint is that the steps cannot pass each other, and that is exactly like the fermion problem again. Okay. So you can actually again write down the propagator or just write down at a given. So for instance, I mean, if you look at these steps like that. You can also think of them as, the VCS walkers, for example, just a Brownian motion which do not intersect each other, okay? And then if you ask, this is time flowing in this direction, and this is space. And if you take a fixed time, and you ask what is the joint distribution of the positions of this step heights, basically. So that is again going to be just GUE Wigner-Dyson distribution, essentially. Yeah, because they satisfy the world line of these step lines. They are exactly like the world lines of free fermions, basically. Yeah. Yeah, this is zero temperature, of course. Yeah. I don't know. That's an open question. That's an interesting question. Yeah, if you can do finite temperature, yes. Yeah. Sorry.
Presumably, I think if you look at the bulk,
yes,
that's the same as if you had started with a periodic box.
Yes.
Behavior. And
that's true, absolutely. That's absolutely true. So because bulk, the sign kernel is just simply phi kx is to the power ikx, essentially. So you get the sign kernel trivially from there. Okay.
Yeah, and presumably then in 2 dimensions and 5 dimensions, the decay of the pair correlation
Yes.
goes like 1 over x to the 2d or x
Exactly.
to the,
Absolutely. Yes. Near the bulk. Yes.
yeah, I was talking yesterday about this rigidity. I think we need a little bit more than that
Right.
faster decay in higher
Oh, I
dimensions.
see. I see.
And I'm not sure whether it just may be true for the ground state of the fermions,
Right.
that it might still be true, even though the decay goes only like
I
1
see.
over x to the 4.
Yeah, that's an interesting point. Yeah, absolutely. That's true. Yeah. In fact, I mean, coming back to your talk, I mean, if you look at, the question you were asking is that if I take, if I take in the bulk, let's say in the context of just the GMT, I mean, GUE eigenvalues, that if I take, just a little box here where L, box size L, is of order the bulk separation between the eigenvalues. Okay, and I ask, how many particles are there, and I look at their variance or even the full distribution. So the variance, of course, goes like log L there, and then, of course, your result with cosθ, where you prove that it was actually Gaussian distribution there. So what we have done recently is to, when you take this L, not just on this bulk scaling, but you take a bigger box. In fact, I mean, people did simulations. What they find is that if you plot this variance of the number of particles inside this box minus L2 plus L, as a function of L, okay. So first it grows, and here, of course, when L is of order n to the power minus half, it of course grows like log of NL. This is n is the number of n is fixed. It's not the density fixed, but it's n is fixed basically. It goes like log NL as you would expect from your results, and then it grows up, and then at some point it just drops very sharply. And why? And this is exactly root 2n. And the reason is because if you take this object as you increase, so what happens is there's more and more fluctuations, of course. And but then when you go beyond this within a semicircle, then of course they are very happy to sit over the semicircle. So they don't, the variance just drops basically. Variance just goes to 0. And so what we could do is actually recently, again this is separate work I didn't talk about here, you could actually calculate this full variance over this, over the all range. So what you find is small arguments, it goes like log L, and you can actually, and again, if you look at here on a finer scale, you see there's these oscillations, and you actually see that there is universal behavior there. And moreover, you can calculate the full distribution also, large deviation functions, which reduces to Gaussian when the box size is very small, but when the box size is large, it is a non-Gaussian large deviation function, and which you can compute explicitly just using the Coulomb-Gas techniques, basically. Yeah.
Just a short question. This basically the question. I have two questions related.
Yeah.
This question is about these oscillations,
Yes.
and the other one is like if you go to higher dimension, this oscillation seems to disappear.
Yes.
Like, can you say something?
Yes, of course. Physically, it's very easy to understand. Why the oscillations? You see, these charges, as I said, they are sort of, sparse, is of order n to the power minus 1/6 is separation as you go towards the edge. So as you go towards the edge, if you look at the density, so basically density oscillates whenever it encounters a charge, density goes up, and then it goes down and goes up, and so you see this finer structure, these oscillations are due to the discrete nature of these particles. Okay. Now what happens in higher dimensions is that they have a more space there, so you don't really, if you go along a line, you don't really encounter that many particles, right? So if you you integrate over these things, so the density smoothens out basically. Yeah.
Okay, so let's think again. We have run a little bit late, and so we meet again at 11:30. 11:30 instead of 11:20.